A damped mass spring system is a classical toy example to understand the differential equation. Anyone with a background in differential equation knows that the solution consists of the superposition of two complex exponentials, each with its own coefficients. If we visualize them directly, then yes, things can get a little bit complicated. But don't you know that, actually, all those complexities can be burned down to a single plot that looks like mountains and valleys? If this is still too difficult to understand, you can even describe the system by a two-dimensional plot of dots and squares. The actor behind this is the Laplace Transform, and this video will peel off the hidden mechanics that makes this thing possible. Let's go. First, we will try to make sense of the circular helix animation. This is actually a way to visualize the possible solutions of a mass spring system in underdamped conditions. The exponents are complex valued, so when they are coupled with time, the matching visuals for them are two rotating arrows in the complex plane. One arrow rotates clockwise and the other counterclockwise, because alpha and beta are conjugates to each other. If we draw a trace of their amplitudes, the shape will resemble a helix with decaying radius. When those two solutions are superpositioned, the imaginary part goes away, leaving the real part intact. We can compute the Laplace transform of the previous function. If we take its magnitude and make a plot in a 3D coordinate system, it will show up a colorful surface. The peaks correspond to the locations of the poles, and the valleys to the zeros. To understand this shape, take a moment to step back a little. If we move the point along the complex plane, its magnitude will vary. When the point is located at one of the roots of the denominator, the magnitude goes all the way to infinity. The same thing happens when the point shifts to the other root. On the other hand, if the point moves to the root of the numerator, the magnitude will shrink to zero. The poles are the coefficients that lie in the exponent. We can call the real part sigma and the imaginary part omega. In this diagram, the poles lie precisely at the imaginary axis. Therefore, there is no decay in the signal. If I shift the value of sigma to the left and hold omega fixed, the damping in the oscillation will get substantially stronger. Next, we consider shifting the poles to the right of the imaginary axis. In this case, the oscillation amplitude grows over time. If I increase the value of sigma and hold the frequency fixed, the growth becomes significantly stronger. If I hold the value of sigma fixed and enlarge omega in both positive and negative direction, the damping does not change, but the oscillation frequency increases. This shows that the Laplace transform enables us to characterize a system by using the exponent of the exponential function. As with other kinds of integrals, the integral for the Laplace transform can converge or diverge. As an example, consider a decaying exponential. The region of convergence, or RC, is the region where the integral will converge to a certain value. This is best explained by an opposite example. What should we do to make this integral diverge? It is pretty easy. We set s to have larger negative values than minus alpha. In other words, we set the real component of s to be less than minus 2. Look at how the integral explodes with this. Therefore, it becomes clear that the Laplace integral will converge for the real component of s larger than minus 2. To draw the region of convergence, we draw a shaded area to the right of the pole that is limited by the vertical line at the pole. There are two subtle features I would like to point out from the last signal. That signal is causal and stable. Causality means that the signal is non-zero for time after t equals 0. For signals with rational Laplace transform, the right-sided ROC means causality. Stability means that if we integrate the signal from its starting point to its endpoint, the result is a real number. This happens if the signal has a pole at the left of the imaginary axis, and its ROC includes the entire imaginary axis. The decaying sinusoid has a different pole 0 configuration, but the ROC also spans to the right of the pole. What can we conclude from the ROC of the previous decaying sinusoid? First is that the signal is causal, and the second is that it is stable. Drawing the entire physical system every time we want to do something with it seems like a really tedious job. Instead, it is more practical to draw a single block diagram with an h of s term inside the block. H of s is the Laplace transform of the impulse response. The impulse input is defined as the Dirac delta function. It is a special type of signal that is defined with integration. It is not the height of the function that is equal to 1, but instead its integration. Intuitively, you can imagine it as a hammer that hits something for a very brief period of time. The left side of the differential equation is the differential equation for the underdamped oscillator. Solving the differential equation with Dirac delta input is not as straightforward as solving the initial value problem. We first compute the Laplace transform of the differential equation. Then, we single out h of s. After that, we apply the inverse Laplace transform onto h of s to get back to the time domain and obtain h of t. And let's not forget to plot it. You can think of the Dirac delta as a hammer that drives the system response to jump to a certain value before eventually decaying. Remember, the impulse response is not the same as the time domain solution with an initial condition. The impulse response can be used to calculate the output of the system with any type of input. Let's change the input to a unit step function. Think of it as a constant force continuously applied to the mass. Its Laplace transform is 1 over s. We can also use it to compute the Laplace transform of the differential equation and then derive the time domain solution by inverse Laplace transform. And here is the plot after some tedious work. This is one of the many applications of the Laplace transform, which is to compute the solution of a differential equation. In conclusion, the Laplace transform brings us an entirely different perspective to a certain signal. Instead of viewing it in the time domain, we've got the perspective in the s domain. The Laplace transform is also useful to evaluate the solution of ordinary differential equation. I hope this video can help you understand the Laplace transform, though it is not as complete as any standard lesson. Don't forget to hit that subscribe button so that you will always be in the same domain as us. Don't forget to leave your thoughts in the comment section. Thanks for watching and see you next time.